Welcome. In this segment, Anatomy of a TGS Device, Part 2, we shall demonstrate powering some simple loads to show the unregulated behavioral aspects of our system when the energy is put to use. First, we shall demonstrate booting up a TGS device. As you can see, the moment the system turns on, we immediately begin to harvest energy and volts are being produced. Notice, as the utilization of the system increases during the boot process, the voltage level increases. Now notice, as the system essentially winds down the boot sequence, the voltage level produced from harvesting drops. And finally, as our system approaches an idle state, the voltage levels will continue to drop until the idle state is reached, and only the amount of energy harvested at idle will be present. Our first load demonstration will cover the powering of a small traditional incandescent light bulb. Our bulb is connected, and now notice immediately that the voltage drop across this load drops our voltage level from the roughly 2 volts at idle to 300 millivolts. Now we shall have our system conduct some work. Notice the energy being put to use and the lamp starting to glow. Also notice that now that our system is conducting its computing work, it is generating more energy, resulting in increasing voltage levels to apply a higher pressure to push electrons across the lamp. As this process continues, the lamp glows brightly. Now, we shall stop our work. You shall now observe the quick drop in the voltage level at the same time during which the lamp dims. And now, as we approach our voltage level at idle, with the lamp still attached, our lamp is almost completely out. In this demonstration, we will connect an efficient blue LED to the system with a workload that just started. Notice that there is no significant voltage drop noted when connected. In other tests, different LEDs were lit even at idle. Once again, as the system works, our byproduct, heat, is produced, providing us the fuel to generate energy. As the volts increase, our LED grows brighter. You can see how efficient the LED is as compared to the incandescent. The voltage level stays at an increased point across the LED's load. This LED was so bright it was able to focus its power to the ceiling. We shall once again stop our work and watch the volts drop and our LED dim. Now imagine that if this one little unoptimized, unregulated server was conducting a function for the enterprise, whether it be a Web 2.0 server, a database server, or just I shall go legacy tech here, a file server, it will be generating energy and conducting work as long as it is in operation, which could be years. Now further consider such servers with their redundant counterparts, or consider the hundreds, if not thousands, of servers at Facebook, YouTube, and Google, ISPs, or government agencies utilizing our system of integrated thermoelectrics. The amount of energy produced is significant and can assist the enterprise in reducing its energy consumption costs. Recall that all such systems, whether routers, switches, densely packed blade servers, and even mainframes, will always continue to produce joule heat from the work they conduct. Even with the advent of virtualization, cloud computing, low power consuming devices and components available today, there will always be heat unless we move to a fully optical system. Yet even in that scenario, the lasers ICs will too emit heat. The heat byproduct will always be present and will need to be removed anyway, so why not put it to work and have it provide some value before it is removed? Notice that even when we halt our system's processing workload, remaining heat is still present and our system continues to harvest as long as possible. Notice the time it takes for this LED to dim as the volts drop. Our next online segment of the Anatomy of a TGS Device, Part 3, will cover a demonstration of the TGS produced energy to conduct some mechanical work and the shutting down of a TGS server.